Alright, we're going to try to explain via camera phone delocalized pi bonding. This ought to be good. Delocalized pi bonding arises anytime you have a situation such as in nitrate ion, where you have 24 valence electrons, and that forces you to draw some kind of resonance structures. Here you have 3 equivalent resonance structures for nitrate ion because the formal charge on nitrogen is +1 in each of these pictures, and it's 0 for the double bonded oxygen, and -1 for a third bond for each of the NO pi bonds. This shows the unhybridized p orbital from each of nitrogen and the 3 oxygens overlapping above and below the plane of the molecule. And there are on average 2 electrons shared among these 3 bonds, which is basically 2 electrons make up one bond, and we have 3 bonding regions, so overall that averages out to 1/3 of a bond. Here's another picture of that, showing the electrons spread out among these 4 nuclei above and below the plane of the molecule. Okay. Over here, this shows just one of the sigma bonds here between the nitrogen sp2 hybridized nitrogen atom. It's sp2 hybridized, so that it has the one unhybridized p orbital. And here, we don't usually talk about what's going on with the terminal atoms, but in order for this to make sense, we have to sp2 hybridize the oxygen also. So the 2 electrons they share here, head-to-head overlap, that's a sigma bond overlap. So there's one of your N to O sigma bonds. And there would be 2 others, one over here and one over here for the 3 single sigma bonds. Okay. What's going on as far as orbital hybridization and just keeping track of where the electrons are so that we end up using 24 electrons? Well, we have 1 electron in order to form the anion, and here are the unhybridized nitrogen and 3 oxygens. Nitrogen is 2s2, 2p3, oxygen is 2s2, 2p4. So, since in order to have the molecular geometry of trigonal planar, we have to sp2 hybridize the nitrogen. In doing so, that's over here, and to keep track of the electrons from the unhybridized to the hybridized, I put the electron, the extra electron that makes this particle an anion, into one of the 2 p's, which will eventually become sp2s, and an electron from the unhybridized pz into what will become one of the sp2s, so that it eventually looks like this over here. So you can imagine as bonds are forming, it's going to be more stabilizing to ultimately have these electrons in sp2s and an empty pz, which can eventually form pi bonds with the oxygen pz orbitals. Over in oxygen, again, this is just bookkeeping, so to keep track of where the electrons are going, as bonds are forming, the 2s electrons jump into what will eventually become an sp2 and the unhybridized pz. Same thing will happen for the other oxygens, so that when they are hybridized, you have an empty sp2 orbital here. This needs to be empty, otherwise you'd have 4 electrons in the same region of space. So I have to make something empty over here. So this nitrogen sp2 will form a sigma bond with this oxygen sp2. Overall, they'll be sharing 2 electrons. Same deal over here. This nitrogen sp2 will form a sigma bond with that oxygen sp2, and finally this last nitrogen sp2 will form a sigma bond with that oxygen sp2. So that accounts for the 3 sigma bonds in our picture, 1, 2, 3. Now for the pi bonds, and again there's our sp2 head-to-head overlap. A sigma bond is always head-to-head overlap, not above and below the plane. That would be a pi bond. That's these guys. So over here, where do we get our pi bonds from? nitrogen was sp2 hybridized, it has an available unhybridized pz orbital that's going to form a pi bond with the available pz orbital of oxygen, but this can't have 6 electrons in it. It can only share 2 at a time, so 1/3 of the time with this oxygen, 1/3 with that oxygen, 1/3 with that oxygen. Okay. If this doesn't seem particularly satisfying or a decent explanation, that's because there's a much better one, and that's called molecular orbital theory, in which case we don't look at individual hybridized orbitals, we just look at the overall molecule as a whole. This is kind of like a little bit like a molecular orbital picture, although we would also include the sigma bonds in our just overall picture of electron density, but this kind of looks like a little bit like the molecular orbital picture. But here's basically our delocalized pi system. That's considered stabilizing because we have 2 electrons that are shared among 4 nuclei instead of just between 2 nuclei. So the electron density is kind of spread out, and that creates for overall net attraction. Okay. So we'll talk more about this in class.